Assalamualaikum warahmatullahi wabarakatuh. Welcome to BMMA1333 Statics. So today we continue with our next topic, which is equilibrium of rigid body. Okay, so for this topic, today's objective, you will be able to identify support reactions and draw a free body diagram. Okay, so there are some activities that we'll be do together in this session. Okay. So for example, we have this a truck ramp with a weight of 2 kilonewton or 2000 newton each. Okay, we can see it has two ramps here. And there's one ramp, and the back one is the second ramp. Okay, and each ramp is pinned to the body of the truck and held in the position by a cable. Okay, you can see this is the cable here. Okay. Now, how can we determine the cable tension and support reactions? Okay, how are the idealized model and the free body diagram used to do this, and which diagram above is the idealized model? So you can see here, if we draw a representative of the ramp with its equivalent cable, support cable, okay, and support on it, okay, we'll see we'll have the point at which the cable, okay, placed at the support, okay, which is this one at point B, okay, then to point A here, and at the same time the ramp itself is being held by a support to make it so that it can be uh, be placed in a rotation motion, okay, and with a degree of 30 degrees between the support of the ramp itself and 20 degrees of the x-axis on the support A, okay, and it has a a centroid, okay, center of gravity G, point G, okay, that is a distance about 1.5 meter between support A. Okay, this would be the how we draw the ramp itself, and the third drawing is we call as the free body diagram, okay, which we remove the support itself, okay, and we change it to a representation. Okay, we have AY and AX that represent the support, okay, uh, of the of the ramp, and also T, which is the tension cable that's holding it, okay, and and then we draw the the equivalent, okay, with all the weight of the ramp, which is 2000 newton, and all the dimension, okay, and all of this is we call it as the free body diagram, or FBD. Okay, another example is for example, these two smooth pipes and having a mass of 300 kilogram, supported by the tines of the tractor fork attachment, which is this is we call it as the tine. Okay, okay, and how can we determine all directive forces? Again, we can use an idealized model and a free body diagram. So this we call it as the idealized model, IM. Okay, we draw the pipes, okay, with all the dimension and the degree with which the tines hold the pipes, and then finally we draw with the FBD. We call this as FBD, which we remove all the unnecessary drawings, okay, and thus represent with the important at which point that intersect, okay, which is T, which is the force that's holding at the time at this point here, and force which is the another angled support which that at one side of the pipe, and also finally the center of gravity or center of mass of the pipes, which is 300 kilogram equals to 2943 newton. Okay, so this we call it as the ideal model, and the second one we call it as the FBD, or free body diagram. So condition, how do we draw a free body diagram? Okay, in contrast to the forces on a particle, okay, the forces on the rigid body are not usually concurrent and may cause rotation of the body due to the moments created by the forces. Okay, meaning that uh, if a part, when we discuss equilibrium of particles, we're talking about concentrating a point. Okay, the whether or not there are any reaction forces, or how about the mass, okay, the center of gravity of the particle. Okay, but for rigid body, we're talking about a whole structure, a whole rigid body with uh, normally at the center would be the center of gravity, and any reaction forces that holding the rigid body itself. Okay, so it's a really it's a bit different with the particle, meaning that we consider all of the necessary forces, okay, that react on the body. Okay, and again, the same as for particle. Okay, for rigid body to be in equilibrium, the net force as well as the net moment about any arbitrary point, meaning at any point of uh, of the rigid body, must be equal to zero, meaning the total forces, whether in the x-axis or the y-axis or the z-axis, must equivalent to the total summation force must be zero, meaning it is not moving in any direction. Okay, it is static, and its total moment, okay, rotation is zero, meaning that the rigid body is not in rotation mode. Okay, it's not moving in a rotation. So what are the process of solving rigid body equilibrium problems? So for analyzing an actual physical system, first we need to create an ideal model, which is this one that we think, okay, would be the equivalent of the actual system itself. Okay, that we draw, okay, with all the necessary information, okay, all the necessary information that we put in. Okay, we draw the idealized model, removing all the attachment. For example, the body of the truck over here, you see, so we remove it. We only consider the part that we want to consider or analyze. Okay, and then next, to draw the free body diagram, we remove all the necessary points, and we replace it with the external forces, okay, showing the active and reactive forces. Okay, and after that, then we need to apply the equations of equilibrium to solve for any unknowns. Okay, so this is an example, okay, showing types of connection or types of support, and what are the equivalent reaction force that represent it. Okay, for example, if you have a cable here, okay, if you have a cable holding it, then the free body diagram drawing it, okay, the equivalent force would be uh, a single force acting on it. If we have a weightless link, then it is almost the same as the cable itself, with the force is either acting towards the support itself, or in towards the away from the support. And next we have a roller, and for rollers we have the support at the point of the contact between the support, okay, with the surface. And if it's a roller or pin in a confined smooth slot, it's the same as the as number 3 as the roller. Okay, at the point of contact, okay, one single force. If it's a rocker, okay, and rocker also same as the both roller and pin. Okay, and if you have a smooth contacting surface, also the same as the, without considering uh, any friction or anything, then we consider it as the same as the roller, pin, and also rocker. For a member with a connected collar pin and smooth rod, then we can it is represented by a single force at the point of contact. Okay, and for smooth pin or hinge, okay, meaning that it does not really restrict the rotation movement, then we have the reaction forces at two reaction forces at Fx and Fy, or we can represent with a single resultant force, okay, with a single reactant force with its own angle at the from one of the axis. Okay, so or if a member fixed connected to collar on smooth rod, then we have two also reaction forces, which is its reaction forces at the point of contact and also rotational moment. Okay, and finally, if you have a fixed support, then all three reaction forces are exist, meaning both the axis axial forces Fx and Fy, and also the rotational moment. Okay, so the rule of thumb here is that if you look uh, the hmm, all of these types of connection and reaction, you will see that if that particular connection inhibits or does not allow a movement in either translation or in actual movement, then the reaction force exists. Mean that, let's say for example, we see here this rocker here. Okay, so this rocker here, by definition, it supports, meaning that it doesn't allow the structure to be moved in one axis. It can only be rotated. Okay, it can only be rotated, but at the same time it can be moved in one another axis, actually in the x-axis. Okay, in the point of contact here with the slope. Okay, it can be allowed to move this area, meaning that if we uh, rock it, okay, the rocker, mean that it can be moved to another position, but at the same time it can also be rotated. Okay, so these two movement, it allows for the structure to be moved. Okay, but we do not want it to be taken away from the surface. Meaning, although by if you think we can lift it, but by definition we don't want the structure to be moved. Okay, we just want it to be at the point of contact. So that's why the direction forces only at just one at the point of contact. So that is if the support inhibits movement in uh, one either in motion or actually in directionally, so then that reaction forces exist. Okay, so you can remember that. Okay, this is an example of an actual support. Okay, in real life. Okay, we have the cable. Okay, is sitting force on a bracket, and we have a roller here. Sorry, no, with a pin. Okay, pin, fixed pin. Okay, and then we have uh, a rocker support, okay, on a bridge, and also we have a girder, okay, holding that's holding the ledge. Okay, I think as a smooth contact surface. Okay, or a floor beam of a building welded together and thus form a fixed connection. Meaning that it doesn't allow any rotational movement, it doesn't allow any translational directional movement in either axis. Okay, then we have a fixed connection. Okay, okay. So this is an example. Okay, we have a, a beam with a fixed support acting on it. Okay, and there is a force of 1,200 Newton acting on it. A distance from 2 meter from one at the wall. It is holding the beam at point A. So when we draw, so first step is we draw an outline shape. Okay, we can draw an outline shape of the beam. Okay, and eventually the be isolated or cut free. Okay, from this constraint, meaning that we don't have the constraint. Okay, this wall, which is this one, we remove it. Okay, and we have and this remove is free. Okay, so then we draw all the external forces and couple moments, relevant couple moments, including the applied loads, support region, and weight of the body. Okay, so in this case, the weight of the body is about 1 kilogram. Okay, which is 981 Newton. So we draw the mass, okay, of the beam. Sorry, it's not point, it's 981, and we have the applied load here, 1,200 Newton, and we have, because this is a fixed support, So it doesn't allow any movement in translationally, meaning in axis both x and y. Okay, and it also doesn't allow for any rotational movement. Okay, so that's why we get the that's how we get the free body diagram. Okay, in the end. Yeah, and also don't forget the relevant dimension. Okay, so next we label the loads. Okay, and also the dimension. All known forces and couplements should be labeled with their magnitudes and direction. Okay, and unknown forces or couplements, we use letters, for example, AX, AY, MA, meaning that the moment at point A and indicate any necessary dimensions. Okay, we put in the information which is this would be the effect of the applied force acting on the beam. This is the effect of gravity, which is weight or mass, okay, on the beam itself, and this is the fixed support acting on the beam. Okay, and also the dimension, which is 3 meter, and this is 2 meter. Okay, and the rest of the dimension of the beam is 6 meters. Okay, so this is a few examples of diagram, okay, showing above. Okay, and you can actually see the support that I just shared with you. Okay, so if the rule of thumb is simple. If that support inhibits or restrict movement in either direction, or movement rotationally for rotation, then that support has that location has its reactive force. Okay, so try to remember that. Okay, so this is a quiz. Okay, if a support prevents translation of a body, okay, meaning it prevents translation, then the support exerts it prevents translation. Okay, meaning movement. Okay, then the support exerts uh, either a couple moment or force. Okay, either it's both A and B. Okay, the answer is B. Okay, it exerts a force on the body. Okay, internal forces are either shown on the free body diagram of a whole body. Okay, we often the internal forces rarely. Okay, we only consider the the external forces acting on it. Okay, not the internal forces. Okay, mean that if it's a if for example a tire, for example, okay, placed on a car, okay, then we place it on the road. Okay, so that tire with its own internal pressure, we we rarely show it on the free body diagram. Okay, because we can say everything is in equilibrium, so we rarely show the sometimes goes to never, but it depends on some cases. Okay, but we only consider external forces acting on the rigid body. Okay, this is an example. Okay, with an operator applying a vertical force to the pedal. Okay, and then the spring is stretched every time force is applied to the pedal. The spring is stretched 37.5 millimeter, and the force in the short link at B is 100 Newton. So we need to draw an idealized model and also a free body diagram of the foot pedal. Okay, so this is how we draw the idealized model. Okay, with the foot pedal here being applied. Okay, stepped on it, and then the spring is stretched to 37.5. Okay, this is the spring is stretched to the vertical force. Okay, the pedal and spring is stretched to 37.5, and the force in the short link, which is this link, is 100 Newton. Okay, the string is stretched to 37.5. So when we draw the free body diagram, okay, we can have this is the 100 Newton represented. Okay, and the distance we draw the dimension, everything, and 150 Newton acting on the spring itself, and also which is which is being provided, and also the fixed the roller support, okay, the pin support, okay, at point A, X, and Y, which is this one. So as you can see, actually this the at point A, the support does not restrict rotational movement. It only restricts positional movement. So that's why you only draw the AX and AY reactive forces. Okay. So this is another subconsequence. If the beam, okay, with this question, if the beam and the cable with a frictionless pulley at D, frictionless, okay, support an 80 kilogram load at C, supporting an 80 kilogram load at C, in the free body diagram of only the beam, if just the beam, there are how many unknowns? How many unknowns that we can see here? Okay, what will be the unknowns? How much unknown? Okay, first we have the support here. Okay, a pin support would have AX and AY. If we know the weight of the beam, we would write it. For this one at C, we know that the load is 80 kilogram, so it's 80 kilogram times 9.81 Newton. And also we have the pulley here. So the another pulley would be another uh, uh, exerting a force on it. So we call it as F E. Okay. So how many unknowns that we know that we don't know? Okay. We have 1, 2, 3, and 4 in total. So that will be, does it have any the couple moment? It doesn't have any couple moment because the support itself does not restrict rotational moment. So the answer would be D, which is 4 forces. Okay. Okay. Next question. If the directions of the force and the couple moments are both reversed, meaning that the direction of the force is, let's say for example, this way, and the moment is turned that way, okay, what will happen to the beam? Okay, what will happen to the beam? If it's in reverse direction, okay, and also the moment acting, there is a rotational moment acting at 800 Newton meter, okay, somewhere almost near to the middle of the beam. So what would be the answer if it's in this direction and this direction of the rotational moment? The answer would be B. The beam will lift at B, will be lifted, okay, because the force is acting outwards, and also the rotation is clockwise, so then the force will be outward, will lift at B. Okay, so this is a group problem solving, okay, which is you can do. Okay, you need to draw the free body diagram first, okay, the idealized model, and then the free body diagram. We have a crane here holding a load at B, and the load is given here at 6,250 Newton, and it's suspended at B. Okay, it's suspended at B, and the boom, which is okay, the boom is here. The weight of the boom itself is 3,250 Newton. Okay, so we need to draw the equivalent free body diagram. Okay, so then we can draw from here we can just analyze if you want to do we start with the idealized model and then move to the free body diagram, or you can just straight away do the free body diagram, which here we straight away did the free body diagram. We have the boom itself, okay, and also the load here. This is the load weights, and then this is the boom's weight, and we have two reaction forces acting on this, and distance, we draw the necessary distance, and we finally get it. Okay. Okay, next also this is an example. Okay, we need to draw a free body diagram of the member ABC, which is supported by a smooth collar at A and roller at B and link CD. So we have a smooth collar here at A, okay, uh, which allows for rotational movement and also translation at one axis but not at the other axis, a roller here at B, okay, and a link CD which is does not inhibits any rotational movement, okay, and all the necessary information is provided with the force acting on it. So then if we draw the idealized model, okay, so then we can move to the fluid diagram, okay, with the action of the one of the support acting on this, okay, and also over here, okay, because of the rocker and also the fixed support. Okay, now it draws here only FCD, just one. Now the reason here we don't draw the actual D here is because over here we already have a pin. If you see here, pin. Okay, so it makes sense that we do not have to draw the other equivalent uh, support here, because this is just up until here. This is the part of the structure that we are concerned that we want to analyze. We don't have to concern with the whole support. We can just represent it by one force acting between the beam CD. Okay, so detection question. Internal forces are not shown on the figure diagram because internal forces are, okay, what would be the appropriate answer? Is it equal to the zero, equal and opposite, and they do not affect the calculations, negligibly small, or not important? Okay, so the internal forces, okay, often and not are not important for the figure diagram, okay, because we only want to consider the external forces. Okay, so how many unknown support variations are there in this problem? Okay, unknown support, we have one over here, and then we have one, okay, okay, on the reaction forces here. So how many unknown support, okay, are in this problem? The answer is three forces and one couple moment, because also here fixed support does not allow any rotational movement. So the answer is D. Okay. Okay, next we're talking about the equations of the equilibrium and also two and three force members. Okay, so we finished on the first part of free body diagram, drawing the free body diagram. Next, we want to discuss about the equations of equilibrium and two and three force members. Okay, so first a quiz on reading, which is understanding. Okay, so the three scalar equations, summation of fx, summation of y, and summation of moment equal to 0 are incorrect. The only correct, the most commonly used or not sufficient equation of recurrent interdimension. Okay, the answer is C, the most commonly used. And second question is a rigid body is subject to forces as shown. This body can be considered as a, is it a single force member, a two force member, a three force member, or a six force member? Hmm? Okay, we call this as a three force member. Okay, because uh, the force of F1 is equal to F1 here. Okay, the direction, everything. So we call this as a three force member. Okay, so writing the equations of equilibrium. So a body is subjected to a system of forces lying in the x and y plane. Okay, when you in equilibrium, okay, it is static uh, condition, the net force and moment acting on the body are zero. Okay, and these 2D conditions can be represented by the three scalar equations fx, summation of fx equals 0, summation of fy equals 0, and the summation of moment equals to 0. Okay, where point O is at any arbitrary point, okay, at any point. Okay, and also these equations, all three of them, are the most commonly used for solving 2D equilibrium problems. Okay, They're not the most correct, but they are the most commonly. And it's so far it provides. It can be used in most of the conditions that we want to analyze a rigid body. Okay. Okay, so this is a typical application, okay, that we use for the two force member that we want to discuss. Okay, so we call this as a two force member. Okay, and this is also an example. Okay, uh, if an engine at 425 kilogram engine is supported by three chains holding, okay, when it's being lifted up of the from the from the body, from the chassis of the car. Okay, and we want to see what are the braking strength of the chains, so that it won't be exceeded. Okay, so how we can determine the force acting in each of the chain? So we have to analyze, okay, based on the weight of the engine, and then any changes they made uh, with the support itself. Okay, so then we want to analyze it. Okay, so based on the weight, okay, and what are the tensile strength of the chain itself, so then we know, okay, what would be the braking strength that would so that we don't want to exceed the strength of the chain. So it's in some equilibrium problems, okay, we can simplify if we recognize members are subjected to forces at only 2 points, okay, at points A and B and figure below. And if we apply the equations of equilibrium to such to that member, we will determine that the resultant forces at A and B must be equal in magnitude and act in the opposite directions along the line joining the points A and B. Okay, okay. So this is if we go back to the example here, okay, if we go back to this example, okay, so we see here, this is we call it as the two force member, because we see there is a force acting on it, on this, okay, and there is another force opposite of this. Okay, so then we know that this is a two force member, so that's why we represent it as just a single force. We don't draw even the rest of the reactive forces at y-axis. We do not draw it, because we know that at this point, okay, there is a force acting on it, okay, reaction force acting on it, and also at the same time at this point another point of contact acting on the reactive force. So we know that it's a two force member. This is an example of another example of two force members. Okay, so others example of two force members, okay, this one, a crane, okay, with the that holds between the structure and the parts that will be hydraulically changed, okay, moved, okay, and also another crane, okay, with its hydraulic part, and then we know that this is will be a two force member. Okay, uh, okay. Okay, so with this, when we try to analyze a rigid body, it helps with that it would simplify, okay, the analysis. Okay, it would drastically simplify, so that we can proceed to solve the rigid body. Okay, so the steps of solving a two-dimensional equilibrium rigid body. First, we need to establish an x and y coordinate system, and then next we need to draw a free body diagram, okay, of the object under analysis, and finally we have to apply the three equations of equilibrium, okay, to solve for the unknowns. Okay. So important notes: if there are more unknowns than the number of independent equations, then we have a statistically indeterminate situation. So we cannot solve these problems using just statics. Okay. In order to which we have to apply equations that may affect the simplicity of the solution. For example, if we have two unknown vertical forces and one unknown horizontal force, okay, we have two unknown. We have a rigid body here. We have two unknown vertical force and one horizontal force. Okay, then if we solve only fx, we would get the first we will get the to solve the the horizontal unknown. Okay, so if the answer of an unknown comes out negative, then the sense of direction and force is opposite to that assumed. Okay, this is also a good rule of thumb. Okay, when you get the solution to a solution of the when we come to the analysis, okay, and we find that the force is a negative value, so then even though with the direction that we draw, so then we know that the correct direction is the opposite of what we draw. Okay, for example, if we analyze, for example, in this example, okay, and we get, for example, is the value is negative 45 Newton. So then the correct would be in this direction at 45 Newton. Okay, okay. So as long as the magnitude is correct, the direction is just opposite. Okay, so if you try to solve a problem, as long as you know that you understand, okay, the magnitude is when you calculate is correct, then the only value is just the negative value opposite of what the direction that we have, then it is in the opposite direction. Okay, so the magnitude must would be correct, but just the direction is different. Okay, opposite of what we assume. Okay, just an example, we have a 4 kN load at a point at B of the beam, and this beam is supported by pins at A and C. So we need to find the support reactions at A and C. Okay, so if we put the x and y axis in we need to put the x and y axis at the horizontal. Okay, we need to draw this would be the x, and this would be this would be the y, and this would be the x axis. Okay, so determine if there are any two force members, and draw a complete free body diagram of the boom and apply the equations of equilibrium to solve the unknowns. Now if you look here at point C, okay, this C is a pin supporting the beam itself. So we know that the for pin support, okay, it does not inhibit movement, rotational movement, so we don't have the moment reactive forces, but it inhibits one directional, okay, at the x-axis, but it supports at the support is at the, so we know that the support is here. Okay, and this here will be a pin support, but the pin support, even though if we try to draw it here, okay, because it's positioned at this angle direction, we know that uh, we can represent, okay, a pin support either this way or just a single resultant force. So we know that this pin, okay, this is, we call it as the two force member. Okay, because it's acting at the same but opposite direction at both points C and D. Okay, so this would be the free body diagram that we draw. Okay, we have the reaction forces at AX and Y, AY at point A. Okay, the load 4 kilonewton at B, and we have the one force acting, the reactive force acting, FC at C at an angle of 45 degrees. So we already recognize that CD, okay, the CD beam here is the has the two force member. So the number of unknowns at C are reduced from 2 to 1. So we don't have to draw the other reactive forces at point D here. Okay, so using the equilibrium of equations of equilibrium, if we consider at point A the moment, the summation of moment at point A, so we don't have to consider forces AX and AY, just consider the FC and also force at B. So we have the equation, we can straight away solve FC, and we get the value at 11.31 kilonewton. And from there, okay, we can try to, since we already know if we try to solve the summation of forces at x, okay, at x-axis, okay, so we know that we don't know the value of ax, but we do know the value of fc here, since we already solved in the first equation. So we can use it with 11.31 kilonewton cos 45, summation is equal to 0, then we will get the value of ax at minus 8 kilonewton. So this minus value meaning that direction is at the opposite direction. Okay, it is supposed to go this way. Okay, and for axis y, the summation of forces is ay plus 11.31 sin 45 degrees minus 4, which is this value here, equals to 0. Then we will get the AY at minus 4 kilonewton. So again, so this the force should be acting this way. Okay, that is all. But the magnitude is correct. It's just our assumption of the direction is different than from the what we calculate. Okay, that is all. Okay, the answer, if you maintain this value, okay, minus negative ax and ay, you maintain the directional that you draw initially, the assumption. But if you want to change to the answer to this positive, then you have to change the direction to the opposite direction. That is all. Okay. So let's move on to concept quiz. Okay. So we see here for this beam, how many support reactions are there, and is this problem statically determined? Okay, we have if all these forces F, we call this is will be F1, 2, 3, and 4 are known. Okay, we know it, its value. So then we have this is the reaction forces at the, because this is a roller. Okay, okay. So we only have 3 uh, reactive forces. Okay, so is it statically determinate? Meaning, can we solve it statistically? Okay, yes. Okay, the answer is yes. 3 reactive forces, and we can determine statistically. Okay, okay. If the for all 4 forces are unknown, then it will be answer D. But if it's known, then it will be statically determinate. Okay, okay. So if the beam AB is loaded and supported as shown, so how many support ratios are there on the beam? Okay, and is this problem statically determinate? And C, is the structure stable? Okay, so we have a fixed support here. Okay, and at the same time we have another fixed support here. Okay, so how many unknowns will be there? We don't know the reaction here. Okay, and because of this, we know this is a two force member, so we have here, and we also have reactive forces here and here. Okay, Mm, so how many reactions that we have? We have 1, 2, 3, and 4 reactions. Okay, 4 reaction forces. Okay, so up until 4 reaction forces. Okay, uh, so is the problem determinate? Even though we have 4 reaction forces. Okay, so this is not so this is ES. Okay, and C is the structure stable. Okay, do we from here do we see the structure stable? Okay, so this is a hmm, hmm, since we have uh, 4 4 reaction forces. Okay, so is this stable? Okay, the answer is no. Why? Because uh, we have both the fixed support here. Okay, is and then with this force here, okay, would hinder any sorry, my mistake. I I uh, so this is a statically determinate, okay, problem, because we can solve uh, so we have more than we only have 4 equation unknown equation, so we only have 3, so we cannot it'll be difficult to solve with all the 4 unknowns, sorry. So the answer is no, and this is a stable structure. Okay, I was confused with the options of the answers. Okay. Okay, so in this problem, okay, we have a overhanging beam supported by a pin at A and the strap BC, So what is the special, about the strap at BC here? Okay, so we have to find the horizontal and vertical components of direction at A and direction at B on the beam. So first we need to establish the x and y axis and draw a complete free body diagram of the beam. And lastly, we have to apply the equations of equilibrium to solve for the unknowns. Okay, so we know that this is uh, uh, a pin support. Okay, so it doesn't inhibit any rotational movement. And this BC, we know it as the two force member because of its pin here and also another pin here. So we know this is a two force member. So we can just so when we draw the free body diagram, we just put in the applied load, okay, 800 Newton and 600 Newton, and also the applied moment at 900 Newton meter at point at the end of the beam. And also we have the two reaction forces AX and AY at A, and also we have reaction forces at point B, okay, which is the FBC, which is the two force member. So we write the moment equation about point A. So why do we write at point A? The reason why we write at point A is because when we consider first at point A, the equation of moment at point A, okay, we reduce the number of unknown. We only have one unknown, which is FBC here, and just we have two known forces, 600 and 800 Newton. So from there, we can straight away solve and we get the value of FBC. If we consider at point B first, or for rather for that matter at the end of the beam, we would increase the number of unknown forces. So the first strategy is that we have to choose points that would reduce the number of unknowns drastically, so that it will be make it easier for us to solve faster, quickly. Okay, so next, since we already have solved the FBC, we can move to solve the summation of fx and fy. Okay, the summation of fx is, since we already know FBC here, so only two forces that x and the x-axis, which is ax and also FBC uh, at this direction. Okay, here. Okay, so we have to know that. So then we will get the value of ax at minus 3130 Newton, which is, so the correct direction is this way. Okay, we can maintain the value negative as long as we maintain the direction. Okay, and for summation of fy is ay here plus the value of fbc here. Okay, and also minus 600 and minus 800 Newton equals to 0, and we will get the value of ay minus 950 Newton. So the direction is downwards. You can answer either this way, maintaining the direction, or you can answer this way, showing the correct direction. Okay, both methods are accepted. Okay, next we have another attention quiz. So which equation equilibrium allows you to determine force at B right away? Is it summation of fx equal to 0, summation of fy equal to 0, summation of moment at A equal to 0, or any one of the above? Mhm. The answer would be M, A, C here. We can straight away because we remove, when we consider moment at A, okay, so the moment acting on this particular point we have to neglect. Okay, only because remember moments formula, okay, the equation is always force times the distance. Since we consider moment at this, so the moment acting at the same axis at this uh, at our point, we have to consider we have, it is 0 because we cannot consider the distance. Okay, it must have distance. Okay, over here we have distance, and over here we have distance, so that's why uh, we can use the moment is much better to determine the force FB. And a beam is supported by a pin joint and a roller. Okay, a pin joint here, okay, and a roller. Okay, so how many support reactions are there, and is the structure stable for all types of loadings? Okay, we have a pin here. Okay, this pin allows rotational movement. Okay, it allows, so it doesn't hinder. Okay, and it doesn't allow for any translation. It doesn't allow any translation of movement, okay, but it allows for rotation. And we have a ruler here. So this is the type of reaction forces that we have, okay. So is it stable? Okay. Also, sorry, how many support reactions? So we have three. Okay, one, two, and three support reactions. Okay, and is it stable? Is it a stable structure for all types of loadings? No, it depends. Okay, if the loading requires, it does not require uh, rotational movement, then it will be good. If some rotations, then it can be because the roller can actually move, even though it hinders here, but this movement of this can also uh, can be can uh, can affect also. Okay. Okay, some if the loading, if it's in this direction, then some movement of the is allowed, okay. So it depends, okay. So the answer can be yes and no, okay. But in general, loading, if it's just direct loading, okay, then the answer is yes, okay. So but generally yes, generally is the structure is stable, okay. Watching this video, okay, so I hope uh, you can understand a little bit uh, of the equilibrium of rigid body. So some of the questions then you can be answered in your tutorial later on, exercises, okay. So then so that you have a better understanding on how to first draw in the free body diagram, and also how to apply the equations of equilibrium, okay, for the rigid body. So thank you very much and have a great day.